So problem 1 wants us to find a point on the curve, square root of x plus 6 plus 2, which is closest to the point negative 5, 2. So what we want to do here is we want to minimize the distance between our function y and point negative 5, 2. So the easiest way to sketch out this problem is we can easily graph this function. So the square root of x is on your graphs you should know sheet. And all this is doing is taking the square root of x and moving it left 6 units and up 2 units. So we can actually graph this. So the square root of x normally starts at 0, 0. So if we take 0, 0 and we move it left 6 places and up 2 places, the graph now starts here. So what would normally be the origin is now at negative 6, 2. If we graph the point in question, negative 5, 2, well, it's right here. I'm just going to kind of dramatically move it over so we can see it. So it's at the same height as the base of our function, but it's 1 unit to the right on the x-axis. So what we're doing here is we want to find the shortest possible distance d from that point to the curve. And so we can do this by setting up the distance formula. So there were no quantities given in the problem, but we want to state what our, we've drawn our picture, we've stated our goal, now we want to label our variables. So I'm going to call d my distance. X is going to represent the x coordinate of my point, and y is going to be the y coordinate of my point. So if we start with the general distance formula, I can start with the squared version, and I can say, well, the distance squared, right, is the difference between the x values squared plus the difference of the y values squared. And so normally when we write the distance formula, we take the square root of both sides, but by now we've seen that optimizing the squared distance is going to be the same as optimizing the distance. And it's a lot easier to take the derivative of this guy than it would be if we actually used a square root. So now I'm going to plug in what I know. One of the points is negative 5, 2. The second point can be written as x comma f of x. So for my x coordinates, it's just going to be x minus a minus 5. But for the y coordinates, the y value in terms of x is square root of x plus 6 plus 2 minus 2 quantity squared. So before I actually dive in and take the derivative, I can simplify this function down a little bit. But keep in mind when we go to do the domain that notice the original incarnation, because the point has to live on this curve that we're looking for, that's going to affect the domain once I do a little bit of algebra. So if I clean this up a little bit on the right side, I get x plus 5 squared. And then over here, my 2's cancel, they add to 0, and I just basically get the square root of x plus 6 squared. Well, when you square a radical, you just get back what was inside. So the function we're going to actually differentiate here is going to be x plus 5 quantity squared plus x plus 6. But now I need to figure out, well, what's the domain of this function? So because the final point lives on this graph, it can't have an x value that's not allowed to be plugged into here. So what we're going to do is I'm going to use the fact that there's a domain restriction on this guy and set up the domain for x, because x, the variable here, is the same x that's in this guy. So if x plus 6 has to be greater than or equal to 0, we can also see from our picture, right, x can't be past negative 6. So x has to be greater than or equal to negative 6. So that means the domain on x is -6 to infinity. Now when I minimize our distance, right, this is the function I'm going to take the derivative of and find my critical values. So to find the critical values, I'm going to take the derivative of this guy. This requires a chain rule, so I get 2 times x plus 5. The derivative of the inside is 1, and then all I have is 1. I'm going to clean this up before I set this equal to 0, so I get 2x, 2 times 5 is 10, and then plus 1 gives me 11. So this is what I want to set equal to 0. Now I'm going to get that 2x equals -11, and x equals -11 over 2. So I want to make sure that this really is a minimum, so I'm going to use the second derivative test just because this derivative was so easy to take. And I can actually use the simplified version here to take the derivative because this is the same thing as this. And so the derivative of this is just 2. Well, that's positive for all values of x on our domain because any value I put in, which means this graph is concave up everywhere. Oops, excuse me. Yeah. So remember here, this graph is concave down, the original curve we were looking at. But when I graph all the distances, right? So if I take this line to represent this distance, and as I rotate it around the curve, you can see that the distance gets much longer, right, when you're measuring points on this edge of the graph, and it's much shorter when you're measuring distances on this edge of the graph. So this is telling me that x equals -11/2 is a relative minimum. But since I only found one critical value, right, on an open interval, then that means this by default has to also be my absolute extreme. So I'm going to come back here to this important fact. If your domain is an open interval and there's only one critical value, right, then the relative extrema is automatically an absolute extrema. So what we can do here is we can also double check that using the closed interval method. So since the one of our parts of our interval is open and the other part is closed, I can also check the value of these two things against each other. So in the original function, I'm going to plug in -6. And when I plug in -6, I get a y value of 1. So that is the distance, and I'm plugging it into f of x, from this point to this point. It's a straight line distance of 1. And that actually makes perfect sense because it's just 1 unit over on the x-axis. But now, if I plug in the critical value that I found into the original distance formula, I end up getting 3/4. So even though this distance here is 1, right, and to a lot of people that would look like the obvious answer, right, if I actually draw a straight line distance to the curve, there's a point right here, and it, 11/2 is -5.5, right here halfway in between, that distance is shorter than that entire distance of 1. So this is, in fact, an absolute minimum. So the solution, when we plug the point back into the original curve, the square root of -11/2 plus 6 plus 2 gives me the square root of 1/2 plus 2. So the point -11/2 comma square root 1/2 plus 2 is the point on y equals the square root of x plus 6 plus 2 that minimizes the distance to -5, 2. And if we want to add one more step, we can say the minimum distance is 3/4.